Hello and welcome. In this video, we're going to talk about how to graph a radical function. So we're going to define the parent functions for cubic and square root functions and just a general nth root function. We're going to talk about their domain and range, and then we're going to practice graphing using transformations from the parent functions. And we're going to wrap up by talking about how does what we already know about transformations apply to these new types of functions. So let's go ahead and jump right in. All right, a radical function is just a function that contains a radical expression. So it could be a square root, a cube root, a fourth root, but it has a radical expression, and the independent variable, aka x, is a part of that radicand, or is inside the radical. So we're going to first look at the square root function. So we know the square root function, the parent function would just be the square root of x. That has a domain, or that starts at 0. You can think of that 0, 0 as sort of the starting point, and then I'm going to just point out some of the easy to plug in values if I wanted to take the square root, because I always like to start by identifying those key points on the parent function graph. So I can take the square root of 0 easily. I can take the square root of 1 to get 1. The next number I can easily take the square root of is 4 to get 2, and then 9 to get 3. So knowing those starting points or those key points for the parent function will make it easier to graph a modification of the parent function. Looking at this, we can see that our domain, the x values, go from 0 up to infinity. Our range, same thing, go from 0 to infinity. Now, just like with quadratics, it's possible that we could be looking at a modification of that parent function, like this one here. This is the general form of a radical function. So h and k, just like with vertex form for quadratics, are talking about our horizontal and vertical translations. A is talking about our stretch or our shrink. So if we were talking about the domain of the general form, what has to be true of a real number inside a square root? It has to be positive. So if you were asked to find the domain of a square root function, what you're going to do is figure out what value of x makes the inside of that radical equal 0. Or you're going to solve to find the domain x minus h greater than or equal to 0, and that's going to tell you the x values that are included in the domain. Now, if the domain isn't 0 to infinity like the parent function, that means the range isn't going to be the same either. To find the range, you'll use that value that you found for x, that minimum value, and you're going to plug it in for x into this inequality, y greater than or equal to a times the square root of x minus h plus k, and you're going to solve for y. So that's how you can find the domain and the range of a square root function. Now, a cube root function is going to be, the parent function is going to be the cube root of x. Now, if you think about a cube root, you can plug in both positive and negative numbers for a cube root. If I plug in, well, actually, let's look at those key points. I like to start with sort of the middle point. I kind of think of it as a vertex, even though it's not a vertex. The middle point here is going to be 0. If I plug in 0, I get 0. And then I'm going to think through plugging in numbers that give me perfect cubes so that I can take the cube root of them easily. Again, I like to kind of know what those easy numbers are for my parent function. So it's simple to take the cube root of 1 to get 1 and negative 1 to get negative 1. The next perfect cube, so 1 cubed is 1, 2 cubed is 8. So if I plug in 8, which isn't going to fit on this graph, I would get 2. If I plug in negative 8, I would get negative 2. But that just helps you see the general shape of the cube root function, which sort of looks like a flattened out or a pulled on little S kind of shape there. Since we can plug in both positive and negative numbers, the domain is going to be all real numbers. Now, even if we stretch or shrink or translate, which are all things we could do, again, looking at our general form here, that's not going to affect the domain and range because we can plug in and have negative numbers inside the cube root. The domain and range is going to be all real numbers no matter what type of cube root function we are looking at. So let's go ahead and actually just find the domain and range for a couple of examples. And then let's see how we can apply what we already know about transformations to graph functions like this. Okay, so when I look at number 1, the first thing I notice is that the index of the radical is a 2, or it's a square root. What that means is whatever is inside this radical has to be a positive number, because I can't, in the real number system, take the square root of a negative number. So I'm going to set the inside of my radical greater than or equal to 0 to make sure all of the x values I plug in give me positive numbers. I'm going to subtract 3 on both sides. That's going to give me 6x is greater than or equal to negative 3. Divide by 6. That's going to give me x is greater than or equal to negative 1/2. Now, remember, you only flip the inequality when you divide by a negative number. So even though there's a negative number involved, I didn't divide by a negative number, so I don't have to worry about that here. So our domain, square brackets, is negative 1/2 up to infinity. Now, if I plug negative 1/2 in, that'll make the inside of the square root 0. That's fine. We're allowed to take the square root of 0. It's just 0. And then we can subtract 2. To find the range, we're going to look at how this new domain restriction affects our outputs. So to find the range, we're going to say y has to be greater than or equal to what I get if I plug that value in. Now, like I said, by plugging that value in, I'm going to get 0 inside the square root. So that's going to give me that y has to be greater than or equal to negative 2. And I'm going to write that in interval notation. Now, for number 2, we're looking at a cube root. And if we're looking at a cube root, it doesn't matter if we have a negative number inside the radical. The domain and the range are both going to be all real numbers, which we're going to write using interval notation. All right, let's talk about transformations. So everything that we already learned about transformations in previous units, in previous chapters, talking about different types of functions, all of that is still true. High-vo still applies. Horizontal things still happen on the inside of the function, and they are the inverse of what you think they should be. Vertical things still happen on the outside of the function, and they're the original, what you think they should be. So if I have something happening horizontally, you're going to see it inside parentheses, or in this case, inside some form of radical. This would mean that I'm moving 2 to the right. If it was plus 2, I'd be moving 2 to the left. Vertical translations are shifts that happen up and down. This plus or minus k tells me how I'm moving up or down. So outside, so here this would be down 1. Reflection over the y-axis is on the inside, over the x-axis is on the outside. With respect to these functions, that's how this would look. And then horizontal stretches and shrinks, they happen inside, so I'm multiplying that number by x. This is a 3, which means that was a shrink of 1/3. Over here, this is vertical, that's a 4 outside the radical. That means we had a vertical stretch of 4. So all of those things, nothing is changing here. We're just looking at it with respect to a new type of function. And even though all of these are square roots, this would be the same with cube roots and fourth roots and so forth. So let's talk about how we can use these transformations to actually help us graph. Okay, so let's start our graphing talk by thinking about some things that can help us, some strategies that we have used when we're graphing other functions. So it may be helpful to start by graphing the parent function for each of these functions. So I'm going to do that with you on these problems. You don't have to unless the directions specifically ask you to graph the parent function and the new function, but it might be helpful to have the parent function and use that as a guide to graph your transformed function. If you have both of those graphs on your graph at the same time, make sure that you're labeling which is which. Then, if you're looking at an even root, a square root, a fourth root, an eighth root, find that starting point. Again, it's not called a vertex, but you can kind of think about it like that. There is a point where it starts and then it either goes up or down. However it goes, there is sort of a starting point. That's going to be the value that you use with your domain that makes the inside of your even rooted radical 0. Start there. If it's an odd root, like a cube root or a fifth root, find that sort of vertex-like point in the middle where it kind of has some symmetry going on that you can use. Then you may want to make a table. You can use your parent function to transform those values to find the new values of your function, or you can just plug values in, whatever's easier for you. Make sure to pick numbers that make sense. So pick numbers that when you plug them in, you get integer values out. So be logical about how you're picking those numbers. And then don't forget about transformations. If all that's happening is a shift, you can start by graphing that key point and then adjust the rest of your graph based off of that. So let's go ahead and graph the parent function for the square root of x, which is what we're going to be using on number 3. So I'm going to underline this in light blue because that's what I'm going to be graphing. The parent function starts at 0, 0. We talked about those key points. The square root of 1 is 1. The square root of 4 is 2. The square root of 9 is 3. That's all that's going to fit on my graph. So I'm going to go ahead and connect. But having that makes it a little easier to graph my function. So I'm actually going to point out what those values were in my parent function. So 0, 0, 1, 1, 4, 2, 9, 3. Now let's talk about transformations. To get our new function g, what are we doing? We're taking each of the x's and we're multiplying them by 1/4. So transformation-wise, what does that mean? It's in the inside, so it's horizontal. So we are horizontally stretching our graph by a scale factor of 4. That's the only transformation that's happening, the only difference from this function to the first one. So what does that mean I'm doing? It means I'm taking each of my x values and I'm multiplying them all by 4 to get the same output values. So I'm going to take 4 and multiply it by x, and that will give me all of my g of x values. So my outputs will be the same, but I'm going to multiply by 4. So 4 times 0 is 0. 4 times 1 is 4. 4 times 4 is 16. That's not going to fit on my graph. 9 times 4 is 36. That's not going to fit on my graph. But if I just take each of these x values and multiply them by 4, I will get the exact same outputs. Or you can just think through what values can I plug in that I can evenly multiply by 4 and take the square root of. Multiply by 1/4 and take the square root of. So 0, 0. If I plug in x equals 4, then I get the square root of 1, which is 1. If I plug in 16, I'm going to get 2. That means I better not cross this line here to get 2 because I should be crossing at the point 16, 2. So I need to make sure that my graph stays narrow enough to not cross before I get to 2. So there we have it. So I'm going to label that my purple graph is g of x and that my blue graph is f of x. And again, you don't have to graph the parent function. You don't have to make the parent function table. Those are just tools that may make it easier for you to graph the new function. So I'm going to go ahead and graph the parent function for number 4. So again, thinking about those basic values that when I plug in give me nice integer values, I'm thinking about my perfect cubes. So the cube root of -8 is -2. The cube root of -1 is 1. The cube root of 0 is 0. And so forth. I'm going to go ahead and plot those points and then connect them. All right, there we go. And I'm going to label this f of x because that's my parent function. Now let's look at transformations. How is this function g different than my parent function f? Well, there's two things that's happening. There's that 3 in front, so we are vertically stretching by a scale factor of 3, and we are reflecting across the x-axis. And since those are both things that are just being multiplied, the order that you list them in doesn't matter. So you could say reflect across the x-axis and then vertically stretch by a scale factor of 3. So what does this mean? This means if I plug in the same x values that I would normally plug in, I'm going to multiply my outputs by 3. So what's happening here? I'm taking my normal cube root of x and I'm multiplying them all by 3. So for g of x, I'm going to multiply each of these numbers by -3. Or you could think of it as I'm plugging -8 in, getting -2, and then multiplying by -3. So if I plug in -8, I'm going to end up with -3 times -2, which is 6. If I plug in -1, I'm going to end up with -3 times -3. Sorry, -3 times -1, which is 3. If I plug in 0, -3 times 0 is 0. If I plug in 1, -3 times 1 is -3. If I plug in 8, -3 times the cube root of 8, which is 2, -3 times 2 is -6. Now I'm going to connect these, or I'm going to plot these 5 points, connect them, and label that part of my graph as g of x. So there I have that graph. Now before we do one more practice problem where we graph a function like each of these, let's go ahead and talk about domain and range. We could still find domain and range the same way that we did on the front of this, acknowledging that any odd root function, the domain and range are both going to be all real numbers. And any even rooted function, we need to figure out what makes the inside of that radical equal 0. Now, that being said, we can look at our graph to also answer this question. The domain on number 3, well, the domain always is talking about what's going on with our x's. So looking at my purple graph, the smallest x ever is 0. And then it goes forever to the right. So my domain is going to be 0 to infinity, including 0. X is allowed to be 0. If we look at number 4, my graph is going forever to the left and forever to the right, which means my domain is all real numbers, -infinity to infinity. Now range, we're looking up and down. We're talking what's the highest and the lowest our graph ever goes. Well, on number 3, the graph is going to go forever up, even though it's going slowly. The lowest it ever goes is going to be 0. So our range is going to be from 0, including 0, square bracket, up to infinity. Similarly, number 4, our range, well, it's going forever up this way and forever down this way. So our range is going to be all real numbers, which we know will always be true when we have some sort of odd-rooted function. All right, let's go ahead and pull up 2 more examples and practice graphing. All right, here we go. I'm going to encourage you to pause the video and to practice graphing number 5 and 6 on your own, and then unpause the video and see how you did. All right, hopefully you had time to pause the video. I'm not going to graph the parent function on these 2 graphs. I think it'll be a little bit more straightforward to just see how you can use the transformation to graph. So for number 5, let's talk about our transformations first. Well, there are 2 things happening, a -3 and a +4. The -3 on the inside means that we have a horizontal translation, 3 to the right. The +4 means that we have a vertical translation of 4 up. So normally our vertex, or our little key point, is at 0, 0. Instead of being at 0, 0, it's going to move 3 over and 4 up. So our starting point is now going to be here instead of at the origin. Now notice those are the only transformations. There's no stretches or shrinks or reflections happening, which means if you know the parent function and how it behaves, you can use that to graph. What I mean by that is normally we have 0, 0, and 1, 1. So my next point should be here. Then we have 4, 2, which means my next point should be 1, 2, 3, 4, 2. And 3, 9. You can use that behavior, the way that it functions, if you can understand and see how to use the parent function to graph. We're just physically picking up the normal parent function and shifting it over. Otherwise, you're more than welcome to make a table. Let me go ahead and set that up. The first x value you're going to pick is 3, because that's what would make the inside 0. That'll give you 4. Then what will make the inside 1? If I plug in 4, that'll give me 5. The next number that I know how to take the square root of evenly is 4. What do I need x to be to get 4 inside the radical? I need it to be 7. The square root of 4 is 2 plus 4 is 6. And then I'm going to see if I can fit one more in there. The next thing I need to make the inside a perfect square is for the inside to be 9, which would mean x has to be 12. The square root of 9 is 3 plus 4 is 7. That one's not going to fit on our graph. So we're only going to be able to fit those 3 points. So we're going to go ahead and connect them and make sure we have an arrow on the end of our graph. Now let's talk domain and range. What is the smallest x ever is? The smallest x ever is 3. What is the smallest y ever is? We can see this from the graph. The smallest y ever is 4. All right, I'm going to go ahead and fill in domain and range here because I know it's going to be all real numbers. I can also go ahead and write what my transformations are. That negative inside means that we have a reflection across the y-axis, and that 8 means that we have a horizontal shrink of 1/8. Now, again, you can either use the parent function or you can make a table of values and plug in numbers. I'm going to go ahead and set up the table for you. Hopefully you already did this on your own. So I'm going to start with just these values, -1, 0, and 1, and then I'm going to see what else I might need in order to just have enough points to make my shape here. So if I plug -1 in, I'm going to get the cube root of 8, which is 2. So -1, 2. If I plug in 0, I'm going to get 0. If I plug in 1, the cube root of -8 is -2. All right, I'm definitely going to need more points than this to be able to have the shape. So what's the next number I can take the cube root of? Well, I can take the cube root of 8, 27. I don't really want to multiply 8 by something to get 27. I think 64. So I'm actually going to plug in -8 and +8, because if I do that, I get the cube root of 64 and the cube root of -64. And 64 is 4 to the 3rd power. So I know when I plug in -8, I'll get 4, and when I plug in +8, I'll get -4. So go ahead and plot those points and then connect them. Make sure you have arrows on the ends of your graphs. And there we have it. So again, make sure you find that starting point. Think about your domain. Make sure that you make a table if you need to. Choose numbers that are going to give you integer values. And then don't forget about your transformations. Transformations will help you graph. Now, to wrap up this video, since we're talking about transformations, this is a great chance for us to review and practice writing a transformed function. And now we can apply this to our new functions, or our new focus for this lesson, which is radical functions. So just like we have done with quadratics and rational functions, we are going to focus on how do we apply transformations, or how do we perform them on a radical function. This isn't new, it's just a chance to practice. So I actually encourage you to pause the video and try and work through these on your own. Remember to write it in function notation and then to apply it to the function. Remember to ask yourself about the order. If the order is wrong, how does that impact how we write the function? And then just do the best that you can. Okay, hopefully you've had enough time to pause the video and look through this. Let the graph of G be the horizontal stretch by a scale factor of 1/6. So that means horizontal shrink of 1/6 means inside the function, I'm going to have 6x. So G of x equals f of 6x, followed by, those are key important words here, a translation 3 units to the left. So I'm supposed to have my translations listed first when I'm talking about things happening horizontally. That means the order is wrong. If the order is wrong, that means I need an extra set of parentheses to indicate that this 6 that happened first, that's going to impact the 3 that happens afterwards. So this is going to be f of 6 times the quantity x plus 3, which means we could simplify this. This is going to be f of 6x plus 18, because that 3 is going to be impacted by the 6. What does this mean for the function that they actually gave us? Well, f is the cube root of x. G is telling us to take what we just did and change x. Everywhere that there was an x in this function, we're going to rewrite it as 6x plus 18. So down here, we're going to have the cube root of 6x plus 18. Last one, let the graph of G be a translation 2 right and 6 up. Okay. So 2 to the right means on the inside we're going to have x minus 2. 6 up means on the outside we're going to have plus 6. Followed by a vertical shrink. Uh-oh, that's out of order. Vertical shrinks and stretches are supposed to happen first, of 1/3. Since it's out of order, that means everything is going to be impacted by that 1/3. So I'm adding that extra set of parentheses in blue to show that that 1/3 is going to impact everything. So I'm going to have 1/3 in front of my function, and this 1/3 is also going to affect this 6 over here. 1/3 of 6 is 2. Now let's actually apply that to our function. So there's a 1/3 inside our function. We're going to have x minus 2. Outside, we're going to have plus 2. And what type of function is this? This is a fourth root. So we are plugging x minus 2 in for x. Everywhere that there is an x, we're going to replace it with x minus 2. In front of the f of x, in front of the function, we're going to have a 1/3. And on the outside, we're going to have a 2. So here is our final answer. So let's recap what we did in this lesson. The first thing we did is we defined what a radical function is, and we focused on square roots and cube roots. We talked about how to find the domain and the range of each of those types of functions. We practiced graphing them and how to use transformations to help them. And then we extended this back a little bit further to transforming a radical function using the tricks that we learned in previous units. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.